Here you go. Yes.
Okay, so this week I have learned about the variational autoencoder. So the first thing is review about the autoencoder. It's just it have the encoding process and decode. So we put in the input and then we encode it into the bottleneck layers, and then we will reconstruct it as an output. So the difference between the output and the input, we call it a reconstruction error. And the variational autoencoder is similar to the normal autoencoder, but it has something different because it provides a statistic manner in the latent space, and the output of the variational autoencoders mostly is the probability distribution. So and the variational autoencoders learn to generate some new data. It's use KO divergence as its loss function to minimize reconstruction loss and latent loss. So instead of encoding process, it will be the probabilistic encoder. It will have it's different from the normal autoencoder, which will have the mean and the standard deviation to encode the input, and then the decoder of the variational autoencoder will decode the information that we store in the latent as a latent vector to produce the probability distribution of input. So the next thing I learned about is the loss function. So the loss function of variational autoencoder will have two main parts. It's a reconstruction loss is the similar as the normal autoencoder in the divergence loss. It will compare the latent vector and the zero mean, and it will inform us when the model producing the latent vector not in the desired distribution. And so the reparameterization trick is we use it when training the variational autoencoder due to the inherent randomness of the sampling operation. So when training the autoencoder, the backpropagation may not work properly. So we use the reparameterization trick to use the necessary to introduce the necessary randomness for sampling, and so the sampling operation can be differentiated, and we could take when using the reparameterization trick, we can take the derivative and optimize the approximate distribution. So here is a example of the difference between the normal autoencoder and the variational autoencoder. So like the mean vector will show us the point here, the point of the output, and the standard deviation will show us the area that the encoding of the input locate in the which area. So it will show us that. So yeah, so instead of pointing in the specific point, like the specific input, it will show us the area, like the distribution, like the encoding of the input locate. And this is another example of using variational autoencoder. So instead of like point as this point, we as using the variational autoencoder, it will show us the distribution, like where the point is, but not like exactly the point. So yeah, so we can, and this is another example. So like it show us the smile at the during this area, and it will, and the skin tone, the gender, and so on. So it will create a vector, the lantern vector, and then it will, when it have that vector, it will use it during the decoding process to decode as an input, and then we can make the output like, yeah. And this another like example. So it's just using the technique of the variational autoencoder to interpolating the handwriting number digit. Yeah, so we can see like it's like the number, like it's a number 5, and then it's gone. So we can like interpolating the hand digit. And this one you also using the technique of the variational autoencoder to for the facial expression to, so like what is the smile like here, and this is not smile or sad, something like that. So yeah, so yeah, that's all I learned about a variational autoencoder.
Yeah. Awesome. Yeah.
You like, I also, I'm not, all I know about it is just like the basic. I will learn more about it later.
Yeah.
Yeah, this is
Yeah.
a good place to start. Reminds me when
Mhm.
I there's actually I forgot actually some about the stuff that I learned when I first learned about it. Like with the reparameterization trick,
Mhm.
could you explain that again? Because I'm a bit confused, like how it was different than how the back propagation is different than when it generates the distributions in latent space. Does that make sense?
About
I'm so
the,
confused.
yeah, so I'm right now, I'm not really like no really sure about it, but
Yeah. I can go over it. No
yeah,
worry. So for um, so here's the variational autoencoder. You have an input and code it. Instead of a fixed line space, you have a probability distribution. And you create a sample. When you have a decoder, you have the output. And you try to minimize the difference between the input and the output. That's the first one. The second one is going to match this probability distribution with the k-added variance. Okay, and then this just really quick. And there's a problem with variation autoencoder when you do backpropagation is that when you feed forward, you can take a sample from the probability distribution, but you cannot do backward. So you can't go from one single sample into a probability distribution. You can go probability distribution to one single sample, but you cannot go backward. And that's one of the problems they have. And what they have to do is you have to reparameterize the latent space Z. So this sample latent vector, you have a mean and you have a standard deviation, you have probability distribution. You create one sample, to Z. So Z is a function of the mean and standard deviation. So it's a function of two variables. In this case, here again, this is pretty much the same thing. This is the latent space, one single sample of latent space. It's a function of two variables. One of them is the mean, and the other one is the standard deviation. And this one is just the decoder. So this is the original form, and this single sample of latent space is a stochastic node, while the other variables, the mean, the standard deviation, the decoder, they are all deterministic node. And what I mean by that node is that when you say deterministic node, if you have a same input, this first neuron, second neuron, the same input, you have the same set of weight, you have the same set of bias, you just get the same output. So this is the first run, you get the same output. The second run, you have the same input, the same weight, the same bias. You should also get the same output. That's deterministic. But for a stochastic node, even when you have the same input, first neuron, second neuron, you have the same weight, you have the same bias, the same activation function. However, the first time you run it, the second time you run it, you have different output. And the main reason because this is a probability distribution. So if you run it like 1,000,000 times and then you plot it out, you're gonna see the correct distribution. But if you just a single few times, you run it individually, you will get different output. And so from that, so this is the original one, because that's we have a problem because this is stochastic node, and you cannot perform a partial derivative or a backpropagation on a stochastic node. So what you do is you reparameterize it. Instead of z is a function of two variables, a mean and a standard deviation. You put z become a function of three variables, a mean and deviation, mean a standard deviation, and another variable we call it epsilon. And this reparameterization is, I think it's taught in multivariable calculus. This doesn't really matter. What all you need to know is that by reparameterize it, you push the stochastic node from here, which is blocking the way. You push it to this side on an epsilon variable. So when you do backpropagation, you can still go to deformation through the mean and the standard deviation. Yeah.
So if I understand it correctly, so if you generate random variables, you can't backpropagate through them because there could have been more than one answer for the same starting point. So instead of having a z describe a distribution, or I'm trying to figure out how to word this, you basically have epsilon, which is a standard distribution, and you are transforming that by epsilon and x. But when you trace back and see which variables give you the best fit, you're modifying epsilon or x, which don't describe probabilities, but you add the probability after them. Does that make sense?
Yeah, I think that's what they do. Yeah.
It's hard to word. I understand what's going on in my head now.
Mm,
Okay.
You get it mentally, yeah. Like I think I explained this math before, but
You did, but I forgot.
Yeah, it's fairly complicated. And yeah. And like also like this trick itself is like required multivariable calculus, which is really hard mathematics. Yeah, that's the main idea. Yeah, just push the stochastic node to the sides, and then you have this smooth way to do backpropagation. Yeah, and then I guess this week I just went a little bit more of the variational autoencoder. So some of them are pretty the same as Phuong, but let me see. So the main, I get one on the big picture. So the main idea of an autoencoder, variational autoencoder, like the same boat, is that we want to recompress the data. So the data is in high dimension, right? But with the same data, we don't need a high dimensional space to describe it. You can describe just this type of three-dimensional data. You can fit that into this two-dimension piece. Same here, you have this is data in three dimension, but you can kind of fit this in this two-dimension piece. So that's one of the idea. I think one of the Cal granted students is doing this too. You reduce the dimension. It's the same. You describe the same thing but using low dimension, and you can easily do that. So that's the whole point of an autoencoder. You have an input, you have output, and it's the bottleneck. So the input and output itself not that interesting, but what we care is the bottleneck right here, the latent space, because it's a compressed presentation of the data we're interested in. And this is autoencoder with different latent space dimension. this bottleneck, if you have this is the input image, if you have two dimensions, so if two dimensions on the bottleneck, you can see we have also the same thing, but reconstruct it. And then this is kind of fuzzy image. If the lattice space is very small, then once you increase the lattice space, it gets clearer and clearer. So it has the ability to learn the underlying pattern of the data, but there's some change to it. And that's what we're interested in. That's the change thing. And so same here. Another application of autoencoder is that you change from this high resolution image into this low resolution image, but it still captures the main patterns of the image. And that's what we want to do. You lower the dimension, but you still keep the important features. Another application is the denoise autoencoder. I did this before. You have a noise, and then you put it into an autoencoder. Then you train this, but not the original one, but you train with the original image. Then you can have the ability to denoise noise image. And on the same page with denoising, you also have impinging. So if you have a block out like this, and you train it so that it's able to fill the blank of the picture. That's one of the application too. And also another application, watermark remover. So it is only capture the underlying the most important feature, and it just delete out what's not important, depending on how we train it. And when I talked to this before, reparameterization, variational autoencoder, and then deterministic nodes, stochastic nodes, trick. There's another. So this is regular variational autoencoder, but then there's a specific type of variational autoencoder, and they call it disentangle. All they do is, so this is the k-outer version. You want to match the probability distribution to the normal distribution of the Gaussian distribution. This is just the reconstruction loss. So they add this hyperparameter b beta into the k-outer version loss, and they're going to control how much it does, how much the k-outer version loss contributes to the total loss of the variational autoencoder. By doing this, I have the paper link down here, by the way, in case you're interested in. By doing that, what they claim is that with this disentangle variational autoencoder, they're able to extract features more specifically and better than a regular entangle autoencoder. So in this case, this one's gonna look more fuzzy, and it's not as good as this. So in this case, for example, they specifically target into room ID. So the background, this background of this is a head, by the way, and the background gonna change like dramatically from this blue theme to this green theme, for example. So when it turns left, so I would assume this is the original image. We have the wall on the right and the wall on the back. Then the wall, you gradually turning left, so you can see more of the wall on your left. And turning right. And I guess like you gradually turn right, and you see more of the wall on the right. That was not so obvious. But this one is more obvious. The distance looks a lot more obvious. Like you can see it's big at first and smaller and smaller when you zoom out. And like for example, object ID is turned from a balloon into a hat, something like that. So it's able to specifically target specific feature in with this rectangle.
Wait, Triet, I'm a bit confused here. So,
Yeah.
what do you mean by entangled and disentangled? Did you explain
Yeah.
it in a previous slide?
This one, yes, this beta right here, yeah.
What does that mean?
This means how much do you want the k-outer version to contribute to the loss function?
Okay, so does entangled mean more KL divergence?
No, it doesn't have to be more. It can be more or less. It means you can control that. So if it's not, it's like the same. So it's yeah, if you can change it, it's proportional, then it's disentangled.
But wait, what distinguishes an entangled autoencoder from a disentangled autoencoder?
With an entangle, so entangle is the regular variation autoencoder. And for the regular one, the loss function doesn't have this beta. So exactly the reconstruction loss and the KL diversion.
No, I mean disentangled versus entangled. What's the difference between those two?
Yeah, entangle is the regular one, and disentangle is this one.
So disentangled is the same thing as a variational autoencoder, and then an entangled is just a regular autoencoder.
No, entangle variational autoencoder is the regular variational autoencoder, and disentangle variational autoencoder is this one.
Wait, is this just describing the the divergence within the hidden space?
Sorry, just real quick.
I'm sorry, I'm confused.
Yeah, yeah. Oh, sorry. Okay, let me go back to it quick. Okay, so you know the regular variational autoencoder, right?
Mm-hmm.
This is the regular one. Okay. Now, if it's the regular one, you don't have this beta over here. Just block it out. So it's just the whole thing with this. So okay, so this is the loss function. So for the loss function, this is the regular one. The
Oh,
loss
it
function.
optimizes beta as opposed to having it be a hyperparameter that you set.
No, it's the hyperparameter. I don't exactly know.
Wait, so the loss function would change beta, but a regular variational autoencoder would just have it be set manually. Is that correct?
No, for a regular one, we don't have this beta. Beta is equal to 1 for the regular one.
Okay, but in the disentangled variational autoencoder will train on which value of beta is best.
Yeah.
Okay, that makes sense.
Then you can control beta so that you
Wait,
can get different features
so do you control beta manually or the loss function does it?
manually.
Then why is it a parameter for the loss function?
Yeah, it's a hyperparameter. You have to
Oh,
change it. Yeah. Just like
okay.
epic and batch number, you have to change it.
Okay, so an entangled variational autoencoder, this beta set to 1, and then a disentangled one that can be set to any value.
Yes.
And that's all the difference between the two?
Yeah, that's not the only difference. Yeah.
Okay, that makes
single
sense. All right.
number.
All right. Yeah, sorry about that.
Yeah, it's okay. Yeah, it's good that you clarified. Yeah. And then they claim that you can target a specific object, like this one, for example, with this beta right here. Instead of this, it's kind of random and like fuzzy in it. And also like this one, they specifically target head rotation. So you go from, looking this way to this, the other way around, get from the right, and then you look straight, and then look from the left. Same thing from the right and straight, like if you look to the left, something like that. And it's pretty consistent to this. While in the regular variational autoencoder, is it's not that easy to do that. There's a little bit of rotation, but it's not that easy. And you can also see, like, for example, this row right here. This guy wearing sunglasses, and this one is completely messed up, for example. But that's like some example of the advantage of a disentangle variational autoencoder. And so the main idea behind this whole autoencoder and variational autoencoder is that we are able to take this very complicated image with very high resolution pixel. We're going to go ahead and convert it into a low dimension space, a later space technically. But we still capture the underlying pattern, the important features. So this is the row, this is the red line, things like that. And we use this to train on machine learning. So, well, this one you can use this to train a machine learning too, but it's just one image, and it's pretty much impossible to train a really big model with large data on this. It's computationally expensive, and that's impossible. But if you're able to, that's one of the problems too, by the way, in machine learning. If you have like unlimited computational power, you can pretty much like solve everything, but we don't have that. So one of the problem, one of the way we better that problem is that we convert this high dimension thing, very complicated thing. We convert this to this, a very low dimension. It still capture the most important thing, but it's easier to compute. Once we have that, we can put in the machine learning and we can learn a lot easier and faster. Yeah, that's it. Right? I mean, any concern?
Okay, so I think you already answered this. So beta is not trained variable, so it does not change as the network learns. It's set beforehand, right?
There's actually different ways to do it. So I know after later they have the ability to like save the model. Like this is called checkpoint, by the way. And they save the model and then you can continue training the model later by loading the weight and the bias from that model and continue the training. I know that it
I
says.
yeah, I actually read a little bit about that as I was investigating some other stuff. So
Mhm.
with the earlier also with the slide with the head turning, what was changing the turning? Was it just different areas of latent space where one dimension was head turning and the other one was type of face?
Uh, I'm not totally sure about that, but I think they're just changing the hyperparameter, the beta one.
Oh, so by changing beta, you get the head to turn slightly. But in that
Yeah,
case, how does it turn with the regular autoencoder?
well, you can't target it specifically.
Okay, I think what's going on is that this is the latent space, and there's two dimensions, and one dimension is type of face, and the other dimension is rotation. I could be wrong though.
I'm not, I'm
Does
not too sure about it, but yeah,
yeah.
something.
Yeah, I think I have any other questions other than that. That was a good presentation.
Yeah, yeah. Thank you. All right. Oh yeah, I forgot. The next one for Phuong is gonna be against model. Yeah, the next week presentation against model. I mean, I presented before, but yeah,
Okay.
good one to know. All right, I'll see you guys next week.
All right, sounds good.